Hello friends. In today's class we are going to talk about an integer variable help in synchronization called semaphore. Welcome here and we are talking about semaphore and few points related with the semaphore. As I already told you that it's a variable that takes an integer value. Okay, this is considered as one of the operating system resource. Semaphore operation execute in kernel mode implemented by Dijkstra. Okay, so these are the very quick point about semaphore. So okay, the few things that required to explain you that it's a variable. It's a like a normal integer variable. Semaphore is also a variable. Is a variable, and the value it does take here in this case is the is integer value. Okay, it is treated as one of the resource of operating system that if a process required resource or the synchronization among processes, then this resource to be used. This operation semaphore operation, we have two main operation, which is wait operation and signal operation. Okay, so we have already discussed that that these are the major source of the interruption the major source of preemption is interruption, and that is the reason that execute in kernel mode and with no preemption. Okay, the Dijkstra was the implementer of this semaphore. So it's a tool, and we have to synchronize the process activities. Okay, so synchronization is a tool. It's a synchronization provided more sophisticated ways for process synchronize their activity. S is an integer variable, and we have two operations over here: wait, signal. Okay, so now we have wait. There are few terminologies are there: wait, down, or P, and we have another one as a signal, and then we have up, or we have a V. Okay, this P and V are basically the term that is the Dutch term, and the meaning of this is probeer. Okay, the meaning here in this case for P is probeer, and V is warhog. Okay, so probeer is for try, and warhog is for increment. Okay, so we have the Dutch term as probeer. I don't know whether it is the correct pronunciation or not, and this is warhog. Okay, so these are the Dutch terms, and the meaning is try and increment. Now, the implementation point of view, there is a definition of wait operation that wait S is if S less than equal to 0, then there is a semicolon, and that is equivalent of the busy wait. Okay, so if S less than equal to 0, if the value is less than or equal to 0, then do a busy wait over here, and signal operation just says that S plus plus. Okay, so very simple that if you are getting the value as less than or equal to 0, then you have to do the busy waiting semicolon, otherwise decrement it, otherwise signal is S plus plus. So this I have written wait down and P, and signal up and V. We have two categories of the semaphore here in this case. The first category is the counting semaphore, where it can take unrestricted domain, and unrestricted domain means it can take minus infinite to plus infinite value. And in binary semaphore, the range is only between zeros and 1. It is same as mutex lock. Let's see an example over here to explain you what exactly happened and how this synchronization happened. And we have taken a sync variable which is initialized to 0. So we have created a semaphore with sync h sync variable, and currently the value here in this case is 0. Now, so S1 and S2 to be two statements are there, S1 and S2, and we want that S2 to be executed later. Now, this the weight sink has been called over here, and in this case, it will just see whether if s, y, and ch, this variable is less than or equal to 0, and if it is there, then it will do the busy waiting. Okay, busy waiting. So yes, it is true, and it will stuck over here in the busy waiting, and S1 will be successfully executed, and then it will give the signal, and somehow it will say that increment, and it will make this variable to 1, and then it will come out of this, and finally it will do S minus minus, and it will enter into the critical section. So in the entry section, this has been always checked. Entry section. So in the entry section, it is just putting the value here, in this case, a weight value, and then after it is successfully executing, then S2 will be executed. So that is how the counting semaphore and binary semaphore, and this is one small example of synchronization. Counting semaphore, as I told you, that it can take the value from a range of minus infinite to plus infinite, is unrestricted domain. If the value of the semaphore is after decrementing is negative, okay, if I am getting a negative value after decrementation, right, then it is considered as unsuccessful. The operation, we will call it as unsuccessful operation. If the value is 0 or positive after the operation, okay, if it is 0, quote unquote, and here it is or positive, then it is successful. Okay, so this is the idea of your counting semaphore. Now here, if I have a S value, counting semaphore value as 4, and I'll do down of 4, and it will become 3. S value will become 3. Down of S will become 2. Down of S will become 1. Down of S will become 0. All this will be considered as your successful operation. Okay, why? Because value is here as the definition. After decrementation, it is negative. Then only it is unsuccessful. Otherwise, 0 and positive after decrementation, then it is considered as successful. Up to here, it is successful. Then this is the 2 unsuccessful process available on the stack. Okay, this is one example. Choose the correct alternative. More than one may be correct, and write the corresponding letters only. At a particular time computation, the value of the counting semaphore is 7. Okay, and then you provide 20p and 15v operation. 20p and v for the signal operation completed on this. The resulting value of the semaphore is. Okay, so 7 value is the current value. Then if you do 20p operation, 20 down operation, the value will become minus 13. And after that, if you do 15v operation, the value will become minus 13 plus 15, and that will become 2. So answer for this question is 2. And that is very simple. You can check it out that 4 is there, then definitely up to 4 it will go down. Data structure. Okay, so how the implementation part. So data structure for the semaphore is it is having an integer value. And this is data structure for what? Let me just write very clearly over here that it is for the counting semaphore. So this is for counting semaphore and anti-value, and we have a struct process, a list is there. Okay, and we are maintaining a list of the processes. The list of PCB of those processes get blocked while performing the down operation unsuccessfully. Now this is something different. Okay, now here we are maintaining a data structure implementation point of view. This is the integer value, and this is the list of the process which get blocked. Okay, blocked. Now somehow we are getting rid of the idea of your word busy waiting. Okay, busy waiting we are just getting rid of, because busy waiting is what? Busy waiting is just a waste of your resource, waste of CPU time. We know that there it has to be in the loop and no useful work is done. So semaphore implementation with no busy waiting, and this definition somehow, though I have to write it before it is somehow working on that part, that now we will not have any busy waiting on this. So with that which is semaphore, they're associating a waiting queue. Each entry in the waiting queue must have two data item. Entry in waiting queue. So we are talking about the list actually. Each waiting entry in the waiting queue is having a value, an integer value, and pointer to the next record in the list. So two operations. One is the block and another one is the wake up. So now we will not do the busy waiting. Block plays the process invoking the operation on the appropriate waiting queue. And waiting queue will be associated with each semaphore. So which each semaphore we are associating a waiting queue, and each process invoking that operation will be placed into the waiting queue. Wake up is the another process, and remove the one of the process in the waiting queue and place into the ready queue with no busy waiting. This is the implementation with no busy waiting, and this is about, again, I'm talking about here a counting semaphore. Counting semaphore. Okay, so now what we are doing here is that semaphore, we are taking a variable, a pointer to a variable, semaphore variable s, and we are decrementing it. And we are checking if the value is less than 0, or we are checking here in this case is if it's a negative. Then we add the process into the s pointing to the list, and we invoke the command block. Okay, invoke the command block in this case. Signal semaphore s, and s pointing to value plus plus, we are incrementing it. And if it is less than or equal to 0, if s is still less than or equal to 0, then we remove a process p from the s pointing to the list and we wake up. Okay, so there are some processes still waiting in the queue, still waiting in queue, and we will remove one by one to them. So here, in this is the simple example that if you have a 3-process semaphore starts with value 1, performing down operation, it will become 0 for P1, let's say, and down operation is successful and it will enter into the critical section. Suppose two more process P2 and P3 perform the down operation and it will get blocked. Upon signaling one of the process, if I see that semaphore value is less than equal to, here you can see that if I see, I'll just increment the semaphore value, and if I see one of the process in the list, I'll just wake up and put into the ready queue. This is also a simple question that if semaphore s is having a current value is 12, and the following operation has to be performed on s. So start with this value 12. After 12p, the down operation, it will become -4. After 2 more v, it will be up by 2, and that will become -2. After 8p, it will become again down by 8 and it will become -10. After 1v, this will become down up by 1 and that will become -9. After 4p, that is 4 up, 4 down, it will become -13. 3v, it will become -10. 6p, it will become, after 6 down, 10 will become 6p, it will become -16, and finally 2v, it will become -14. Okay, so -14 is the final value of this. The last variation here in this case is the binary semaphore, where it will take the enum value like from q and 1, and there is still a ql. Okay, so we have already seen the data structure, and rather than writing ql, I will write here struct process list. Okay, I'll just write this notation, that will be better. Struct, rather than writing ql, I'll write here struct process list, pointer to a process list. Now, so here, okay, we are done with this. Okay, I think it's getting repeated. Okay, this binary semaphore, we have done this part, I guess. Yes, now here. So this is the operation of your down operation or up operation, and or p, or here it is p, or here v, or it is implemented as wait and signal for binary semaphore. A binary semaphore, what it will do, it will check the value if it is exactly equal to 1. S pointing to value. S is the semaphore variable, and it can take the value from 0 or 1. So it will check the value S is exactly equal to 1, then it will set it to 0. Okay. If it is not 1, then definitely it is S value is 0, and it will put the process in PCB in S.L and block it. Okay. Somehow a command for blocking it is the sleep. In the previous one, we have not mentioned entirely here this one, that we said block, okay, or we can call it as also sleep. But do not get confused with these two terms, that block and sleep are used alternatively. And here in signal, if S.L is not empty, the first signal is remove a process from P from the S pointing to list and wake up. Else, just make the value to 1. Okay, so that is your down and up operation in case of binary semaphore. One clarification, you understand that if S pointing to value is 1, then it will make it 0. If S pointing to value not equal to 1, then there must be some processes waiting to be awaked. Okay, S is exactly equal to 1, then it will be 0 and your operation is successful. Otherwise, what? Operation is unsuccessful and you put them into a sleep. Here, if S.L is not empty, that means there are, so I was talking about this one only initially. If S.L is not empty, then there are few processes waiting for it. So remove the process and just wake it up. Otherwise, you set the value to 1. So until there are some process, until there are some process in waiting list, semaphore value will not be 1. Semaphore value will not be 1. Okay, it will be keep on waking it up. Okay, so we have three processes P1, P2 and P3, and there is a binary semaphore S having the value 1. So P1 issue the down command, S makes to 0, enter into the critical section. P2 will issue the down command, gets blocked. P3 issue the down command and gets blocked. Okay. So that is about your binary and counting semaphore and this operation that is wake up and wait and signal, which uses block and wake up call. Okay, so here we are putting the process into the S dot list and we are blocking it and removing the process and wake up. So I can understand that I have a two different looking kind of type of that implementation, but more or less the idea of this down and up is same. Putting here, and just we are playing with the values here, that because here minus minus and plus plus, and these are the few example related with this. Okay, so I hope I'm clear with this this semaphore thing, and the main thing here in this case is the implementation to achieve synchronization with the help of this semaphore. Okay, so that's all for this discussion. Thank you.